we're now going to turn our attention to the third type of intermolecular force of attraction, which is known as hydrogen bonding. So we see here that hydrogen bonding is a stronger intermolecular force of attraction than either dipole-dipole or dispersion IFAs. So what is hydrogen bonding? Hydrogen bonding is an unusually strong type of dipole-dipole intermolecular force of attraction. So we're observing hydrogen bonding between polar molecules. However, the strength of the intermolecular force of attraction merits hydrogen bonding being in its own separate category apart from dipole-dipole. It's a stronger intermolecular force of attraction than dipole-dipole forces are. So how do we recognize and distinguish between hydrogen bonding and dipole-dipole IFAs? Hydrogen bonding occurs between a polarized hydrogen on one polar molecule. And that's a key word that I want to emphasize. If you're trying to evaluate hydrogen bonding, you must be able to identify, do I have a polarized hydrogen atom present in a molecule that I suspect may be engaged in hydrogen bonding? So what is a polarized hydrogen? A polarized hydrogen atom is one that is strongly partially positive, unusually partially positive, because it's bonded to a nitrogen, an oxygen, or a fluorine atom. And if you recall, these three atoms, nitrogen, oxygen, and fluorine, are the most electronegative atoms on the periodic table. When they are engaged in a bond with hydrogen, these atoms would be the one that would be pulling most strongly on that shared electron pair, pulling the hydrogen electrons towards their own atom, or the hydrogen electron towards their own atom, and they would acquire, as a result, a partial negative charge and leave the hydrogen atom strongly partially positive. So strongly partially positive, because it's on the losing end of this tug of war for electron density in the covalent bond. So in order to have hydrogen bonding, you must have a polarized hydrogen atom present on one molecule. And that polarized hydrogen atom, because it's so strongly partially positive, wants to attract to negative charge. And what atoms are the most likely candidates for negative charge? The same three atoms that polarized the hydrogen to begin with. So a polarized hydrogen will attract to an oxygen, nitrogen, or fluorine on a second polar molecule, because these atoms have that negative charge, partial negative charge, that the hydrogen polarized atom is looking for. The premier example of hydrogen bonding is water. Water has hydrogen bonding acting as its primary or strongest intermolecular force of attraction. And recall that dispersion IFAs would also be present in water, but they are not the primary or strongest intermolecular force. Hydrogen bonding is. So let's take a look at how we recognize hydrogen bonding, or how you would draw it if you were asked to do so. So right here I have a water molecule. And notice I've drawn the water molecule to emphasize that the hydrogen atoms are polarized in the molecule. So they're drawn in red. All of these red hydrogens are polarized hydrogens. They meet the definition, the criteria that we stated. They are bonded to one of the three most electronegative atoms, oxygen. So these hydrogen atoms shown in red, all of them are covalently bonded to oxygen. Therefore, the oxygen, as the more electronegative atom, is attracting that shared electron pair more closely to its own nucleus, and we can show the partial negative charge that the oxygen has acquired as a result of pulling more strongly on the shared electron pair leaving the hydrogens strongly partially positive, unusually partially positive. So all of these hydrogens present in water molecules would all be polarized hydrogens. So what does a polarized hydrogen want to do? It wants to attract a negative charge. That means that a polarized hydrogen on one water molecule, and let's just kind of circle here so we clearly see water molecule, and a third water molecule. All of the polarized hydrogens are interested in attracting to partial negative charge. So here we have a polarized hydrogen on one water molecule attracting to a partial negative oxygen on a second water molecule. And we show that hydrogen bonding by a series of dots, never a solid line. So you would never replace those dots and put in a solid line for hydrogen bonding. We know that solid line means a covalent bond. Hydrogen bonding is not intramolecular bonding. It's not a covalent bond. It's an intermolecular force of attraction. So we need to represent it differently than we do covalent bonding. And most texts show it as a series of dots, often 3, between the two molecules that are hydrogen bonding. So I see here in the drawing a polarized hydrogen on one water molecule, hydrogen bonding or attracting to the partially negative oxygen on a second water molecule. And notice that the attraction is oriented along the line or axes of the lone electron pair, because that would be an extra rich source of electron density. So this polarized hydrogen is aligning towards that lone unshared electron pair on oxygen. And because oxygen has a second lone pair or unshared pair, we can have a second hydrogen bond forming with a separate water molecule through its polarized hydrogen, as I'm illustrating here. It is also very important to note that if you're drawing it, it is an electrostatic force of attraction, and you would need to show the partial negative charge on the oxygen and the partial positive charge on the polarized hydrogen. That is the electrostatic force that is causing these molecules to stick together. And let me just add here this partial negative charge on this oxygen as well. Even though I haven't completed the drawing, we could extend this hydrogen bonding between large number of water molecules. You'll remember that when I introduced intermolecular forces of attraction, I talked about a piece of tissue paper not being able to attach to a board in its dry state, but that we could change that and cause it to stick if we wet it and put some water on the tissue. And so repeating that, I can now say there is an illustration of hydrogen bonding between water molecules. The water molecules are attracted together, they want to stick together, and it's that force of attraction that's holding the wet tissue paper to the now wet board that has some water on it as well. Notice that the hydrogen bonding can be easily overcome, but then it will reform again. This sort of intermolecular force of attraction is very important in multiple systems, especially biological or biochemical systems. I know you've heard of the molecule DNA, and most of you can recall from high school biology or some other biology class that DNA is a double-stranded molecule, 2 strands that bind together to form a double helix. And that binding together process, not bonding, right, but that attracting together to form the double-stranded helix is mitigated by hydrogen bonding between molecules on the 2 separate strands. So hydrogen bonding is an incredibly important intermolecular force of attraction, water, such an abundant molecule, not only on the Earth's surface, but also within living organisms. So understanding the type of intermolecular force of attraction at play between water molecules is essential. We talked about how intermolecular forces of attraction can affect properties like boiling point, and it is the strength of hydrogen bonding between water molecules that explains why water has such a remarkably high boiling point, 100 degrees Celsius. For a molecule of such small size, water only has a molar mass of 18 grams per mole. So it's this wee little molecule with this tremendously high boiling point for its size. And that is a direct reflection of the strength of the hydrogen bonding, the intermolecular forces of attraction that operate to hold water molecules in close contact. You'll have to give water a lot of energy to overcome these intermolecular forces of attraction and separate the water molecules individually in the gas phase. Let's see if we can't see how well we are understanding hydrogen bonding with a couple of examples. So questions here, and you might be prepared to put this video on pause while you think about the answers. So first question, can ammonia molecules, and a reminder that ammonia has a formula NH3, can ammonia molecules hydrogen bond with each other? If yes, draw the hydrogen bonding, and if no, explain why no hydrogen bonding occurs between ammonia molecules. So this might be a good point for you to put this video on pause while you think about this question and answer it. Can you draw hydrogen bonding between ammonia molecules if you decide that it can hydrogen bond with itself? If you believe no hydrogen bonding occurs between ammonia molecules, what would be your explanation for why it can't? So I'm going to give you a moment to pause here, and I'm going to go ahead and draw the answer while you're thinking about it. So looking at the Lewis dot structure for ammonia, of course you have to be able to look at the structure and evaluate the polarity before you can go on and decide whether or not hydrogen bonding can occur. I recall that ammonia has the Lewis dot structure as shown here. I recognize the trigonal pyramidal geometry that is present molecularly for the shape of ammonia. Electron pair geometry is tetrahedral, but molecular geometry is trigonal pyramidal. I recognize that the bonds between nitrogen and hydrogen are polar covalent bonds. Nitrogen with an electronegativity of 3, hydrogen with an electronegativity of 2.1, making that a difference of 0.9. So these bonds would be polar covalent bonds, nitrogen partially negative, and each of the hydrogens partially positive. So ammonia is a polar molecule. The question is, are these hydrogens polarized hydrogens? Well, what is the definition of a polarized hydrogen? One that is strongly partially positive because it's bonded to a nitrogen, oxygen, or fluorine. And bingo, ammonia meets that criteria. All 3 hydrogens are bonded to nitrogen. That means all of these hydrogens are polarized hydrogens. And let me just redraw, emphasizing with that red color, making them pop, that they are strongly, the hydrogen atoms, strongly partially positive because they're bonded to one of the big 3 electronegative atoms. So what does a polarized hydrogen want to do? It wants to attract to negative charge. And a second ammonia molecule would provide that partially negative nitrogen atom needed for the hydrogen bonding to occur. So I am showing a hydrogen bond between a polarized hydrogen on one ammonia molecule and the partially negative nitrogen on a second ammonia molecule. And again, completing the drawing here and indicating that these hydrogens would also, of course, be polarized. So I see this hydrogen bond happening right here between two ammonia molecules. Yes, ammonia can hydrogen bond within itself. Molecules of ammonia can hydrogen bond with each other, and we've drawn this making sure to include the partial negative charge on the nitrogen and the partial positive charge on the hydrogen of a second ammonia molecule. And let's just indicate here by encompassing that we're looking at two separate ammonia molecules. And now here is our second question. Can dimethyl ether molecules hydrogen bond with each other? If yes, draw it. If no, explain why. And I've given you the structure of dimethyl ether. It has several central atoms, so a little more complex structure. It's an organic molecule, and I've provided you with the structure. Now that you look at it, can you evaluate whether or not one dimethyl ether molecule would be able to hydrogen bond with the second dimethyl ether molecule? Again, I suggest that you put this video on pause and think about that answer. If yes, hydrogen bonding can occur, draw it. If no, explain why. So while you're pausing and thinking, I'm going to go ahead and start with the answer. And my conclusion is that no hydrogen bonding can occur. All right, so no hydrogen bonding can occur between two dimethyl ether molecules. Between two dimethyl ether molecules. And why? You have a 50-50 chance of guessing. So why would that be the case? Because I look at this structure and I see there are no polarized hydrogen atoms present. All of the atoms of hydrogen are bonded to carbon. All hydrogen atoms are bonded to carbon. And carbon is not one of the atoms that strongly polarizes hydrogen. In fact, we've talked about the fact that we wouldn't even consider a carbon-hydrogen bond to even be a polar covalent bond at all, because the electronegativity differences between the two atoms is so small. So you don't have any strongly partially positive hydrogens that would be interested in trying to hydrogen bond with an oxygen, nitrogen, or fluorine on another molecule. So no polarized hydrogen atoms are present. However, before I finish up this discussion, I do want to mention that I recognize that dimethyl ether does have an oxygen atom, and that bond between carbon and nitrogen is a polar covalent bond, so that oxygen atom would be partially negative. And if you took dimethyl ether and added it to water, now we know water does have polarized hydrogens. You could form hydrogen bonding in the mixture of dimethyl ether and water. So I can show here that hydrogen bonding can occur between, let's make this black, between, and let's make this red, keep my color coding constant. Hydrogen bonding can occur between the polarized hydrogen on water and the partially negative oxygen on dimethyl ether. So I predict that dimethyl ether would be able to form a solution with water because of the hydrogen bonding that can form between the two molecules. Water providing the polarized hydrogen and dimethyl ether providing the partially negative oxygen needed for the hydrogen bonding to occur.